Why are large steam turbines so difficult to design? Imagine trying to build a giant machine that turns super hot steam into electricity, but it has to do this perfectly for decades. That's what designing large steam turbines is all about. These turbines are the heart of many power plants, running on the principles of the Rankine cycle, which involves heating water into steam, expanding it to do work, and then cooling it back into water. The challenge is making sure this cycle runs smoothly at a huge scale. First, these turbines operate at extremely high temperatures, often around 600 degrees Celsius, and pressures over 25 megapascals. That's like trying to keep a metal pipe from melting or cracking when it's constantly exposed to such heat and pressure. Engineers have to pick special alloys that can handle these conditions without bending or breaking. They also use advanced cooling methods to keep the parts from overheating. The hotter the steam, the more efficient the cycle, but it also means more stress on the materials. Next, thermal stresses come into play. When the turbine starts up or shuts down, different parts heat up or cool down at different rates. This uneven heating causes expansion and contraction, which can lead to cracks or fatigue over time. Designing turbines to withstand these changes over thousands of hours of operation is a real puzzle. Size is another big factor. As turbines grow larger to produce more power, sometimes over 1,000 megawatts, their rotors and blades become enormous. These long blades are heavy and experience huge forces from rotation and vibrations. Keeping everything balanced and aligned is tricky because even tiny misalignments can cause damaging vibrations or blade failures. The way steam flows through the turbine also matters. Engineers must shape the blades carefully to guide the steam efficiently, minimizing energy losses. If the blades are not designed right, deposits or erosion can occur, which distort the flow and reduce performance. Deposits from impurities in the steam can cause blades to become rough or damaged, which leads to vibrations and less efficiency. Material degradation is another concern. Impurities in the steam can cause corrosion and erosion of blades and nozzles. Over time, these deposits change the shape of the blades and make the turbine less efficient. This means turbines need regular maintenance and high-quality materials to stay in good shape. Flexibility is increasingly important too. Power plants need turbines that can handle quick changes in load, especially with more renewable energy sources coming into the grid. Rapid starts and stops put extra stress on the turbine components, so they must be designed to handle thermal cycling without cracking or losing balance. Manufacturing such large turbines is a complex task, they requiring very precise parts and assembly processes. Every blade, rotor, and casing must fit perfectly and withstand the extreme conditions inside the turbine. Small errors can lead to big issues down the line. All these factors mean engineers have to carefully balance many aspects: thermodynamics, mechanics, materials, and manufacturing, to make turbines that are safe, reliable, and efficient. They use computer simulations, stress tests, and special materials to solve these challenges. Understanding these hurdles shows how the principles of the Rankine cycle are put into real-world action. It's not just about the ideal cycle but about managing the physical realities of high heat, pressure, and mechanical forces. Large steam turbines are marvels of engineering that turn complex science into the power we relying on every day.